Atlantipedia essay, May 29th, 2010 by Dr. Ulf Richter, 1935 to 2006, Mainzerstraße 25, D55270, Schwabenheim, Germany. Abstract. Reading Plato's two books about Atlantis and comparing the described facts with modern knowledge about geology, tectonics, archaeology and technology gives us new insights about how Atlantis looked. This is necessary before we can seek its proper location. We know that around the royal city of Atlantis lay an absolutely flat and even plain, irrigated by a widely branched system of canals that drain into the sea. This plain was formed by alluvial land in a large river delta. To feed such a delta, the area of the whole country must have been at least 10 times as large as the plain. There must have been a chain of high sand dunes along the shore. The hill with the central temple was formed by tectonic forces during the uplifting of a salt dome. The three circular ditches were formed by natural erosion, and the two springs on the central island brought water from the distant mountains. For the irrigation of the fertile alluvial plain, a central organization was necessary, which led to the formation of the high culture of Atlantis, as was the case in most of the world's other early cultures. The canals in the alluvial plain were V-shaped. The excavated silt was used to build dams on both sides to protect the fields against flooding by the tides and from the mountains. The reported depth of the canals shows that Plato's stades must be translated as Egyptian length units, kehet. 1 kehet equals 52.4 meters, and so we get realistic dimensions for the plain: length 157 kilometers, width 105 kilometers, and the royal city, diameter 6.6 kilometers. Tables show the dimensions of Atlantis in comparison with buildings and canals in ancient and modern times. Atlantis has been written about for over 2,000 years. The main source is Plato's dialogues, Timaeus and Critias. There have been many attempts to locate Atlantis, but no one has really been successful. Here is a new attempt to describe how Atlantis must have looked, using Plato's descriptions and the knowledge of our times. This description of Atlantis will be a useful condition for determining its location. 2. The hill in a flat plain. What do we know from Plato's descriptions? I used Berry's translation /1/. The numbers show the references Stephanus' pagination in Timaeus and Critias. 1. The residence of Atlas and his royal palace was situated not far from the sea on a hill, low on all sides, Crit 113c, in the center of the city, which was laid out in a circle, Crit 116a. 2. The circular central island city-state was surrounded by 3 rings of water and 2 rings of land. Alternatively, Crit 113d, 115e. The water rings were used as harbors and had access to the sea by a canal, Crit 115d, and by passages connecting the water rings, Crit 115e. 3. The part about the city was all a smooth plain, Criticism 118a, highly fertile, Criticism 113c, stretching along the sea. Its width from the sea inland was 1.5 times smaller than its extension along the sea, Crit 118a. 4. The plain was rectilinear for the most part and elongated, Crit 118c. 5. The plain was surrounded on all sides, save towards the ocean, by mountains that stretched toward the sea, Crit 118a. They sheltered the plain which faced south from the northern blasts, Crit 118b. 6. The mountain streams drained into a ring canal round the whole plain, Crete 118c, discharging from both sides into the sea near the city, Crete 118d. 7. There were parallel canals at regular intervals, as well as connecting canals throughout the plain, Crete 118e, forming a canal grid. The canals were used by boats to carry wood from the mountains to the city. What can we deduce from all this information? Since the canals flow out into the sea, and ships could enter from the sea into the canal system, the plain could not be far above sea level, and was only slightly inclined from the mountainside to the seaside. A regular level plain, surrounded on all sides by a ring canal and covered by a grid of smaller canals for irrigation and draining, can only mean an alluvial plain. Either it must have been a big lagoon which was filled with washed-up matter, or most probably, it was the delta of a great river. When looking at an atlas, one will find that such large and even plains exist only in the delta regions of great rivers, and were formed by sedimentation from these rivers over thousands or millions of years. This idea is further confirmed by the fact that, after Atlantis was flooded, the resulting mud was a hindrance to ship traffic. Tim 25d. A great river, and there is mention of rivers that flow from the mountains, Crete 118de, must be fed from a large area. One must therefore contradict those who say that Atlantis was only slightly larger than the plain itself. If it were an island, it would have to have been 10 times bigger than the plain, if not more. In an alluvial plain, the soil would have been very rich and fertile, as it is described in Crete 113c. The construction and upkeep of the canals would be an enormous task, which Plato has mentioned as being almost unbelievable. Crete 118c. Managing this task was probably the reason for the development of a central organization, and thus the starting point of the state of Atlantis. At least that is what we believe about other early highly developed cultures that began in big river oases or deltas in order to organize of the necessary drainage and irrigation, e.g. in Mesopotamia, in the Indus Valley, the great river region of China, and the Nile Valley. One could almost surmise that the culture of Atlantis had its origins in roughly the same time period as these other archaeologically studied high cultures, although I will not speculate about the time frame here. Crete 118c, Fig. 1. Plato described the plain as a rectangle, but a perfect rectangular plain, surrounded by small mountain chains on 3 sides, exists nowhere on the globe. It seems that Plato, who never saw the site himself, imagined from Solon's description that the whole plain was a rectangle, and therefore calculated the consequent length of the circumferential canal to be 2 times 3,000 plus 2 times 2,000 for the 4 sides equals 10,000 stades. Critique 118d. Figure 1. The plain round the royal city. But in some translations of Crete 118a is not spoken of a rectangular shape, as Berry and Lee write, but of an oblong shape, Jowett, or of an oblong triangular shape, Spanoth. In Crete 118c, we read that the plain was rectilinear for the most part. That can mean that only a great part of the plain was rectangular and enclosed by the circumferential canal, but not all. And when Plato says in Crete 118a that the plain measured 3,000 stades in length and at its midpoint 2,000 stades in breadth from the coast, Translee, then this seems to be the description of the normal delta form of the plain, namely 2,000 states wide from the sea only in the middle and smaller towards both ends. 3 sand dunes. We saw that the whole irrigated plain could not be much elevated above the sea level. On the other hand, in Criti 118a, we read that the whole region rose sheer out of the sea to a great height, but the part about the city was all a smooth plain, encircling it all about. Mountain chains were only on 3 sides of the plain, not at the seaside. On the other hand, if the circular canal received the streams which came down from the mountains, and after circling round the plain and coming towards the city on this side and on that, it discharged them thereabouts into the sea. Crit 118d. This would mean that the seaside branch of the canal runs all its length parallel to the seashore. In the case of a flat seashore, it would be most probable that the water streams in the canals on both sides of the plain would discharge immediately when reaching the seashore, especially when seasonal high floods were occurring, and not bend in an angle of 90 degrees toward the central water exit near the city. Only a chain of high sand dunes along the coast could prevent the described behavior of the water streams and lead them parallel to the coast. Figure 1. We know those dunes from many parts of the world. For example, at the Atlantic coast of France near Arcachon, dune height 114 meters. At the eastern coast of the Baltic Sea, dune walls 80 meters high. Or at the eastern coast of Lake Michigan, USA, sleeping bear dunes 120 meters high. The condition for the formation of these high sand dunes is a steady, strong west wind vertical, or in a small angle to the coast. Behind the dune wall is usually a chain of lagoons, and these lagoons could have been used by the Atlanteans to construct their canal along the seaside. Such a high dune wall, seen from a boat near the coast, can look as if the whole region rose sheer out of the sea. Figure 2. Figure 2. Sleeping Bear Dunes, Michigan. 4 Poseidon circles. Plato describes in Crit 113d that Poseidon married Cleito, and to make the hill whereon she dwelt impregnable, he broke it off all round about, and he made circular belts of sea and land, enclosing one another alternatively. 2 being of land, and 3 of sea, which he carved as it were out of the midst of the island, and these belts were at even distances on all sides, so as to be impassable for man. For at this time neither ship nor sailing was yet in existence. It is said clearly that these circular canals were not made by man, but by a god, or alternatively, by natural forces, in very old times. Which natural forces are able to form those regular structures? We come nearer to a solution of this problem when we look at satellite photos of the Guelber Richa in Mauritania, Figure 3. This link shows fascinating pictures of regular circular structures, alternating between higher and deeper level, the deeper rings partially filled with water. The height difference is about 100 meters, the diameter of the structure 35 kilometers. The erosion-resistant higher rings are of quartzite, while the central circle is of flat layers of limestone. It is clear that, in spite of the obvious similarity of this structure to Plato's description of the royal city, this cannot have been Atlantis. The Guelber Richa is too great, too high above sea level, 400 meters, and 500 kilometers distant from the seacoast. But it is possible that the circular structure of the royal city of Atlantis was formed by the same process. First, the uplifting of formerly flat rock layers by endogenic forces to a dome-like hill. Afterwards, the erosion of the softer layers, so that the circles of the harder layers remain. Erosion by water is a work adequate to a god like Poseidon. Salt domes can be found frequently when internal tectonic forces press on salt layers, which behave plastically under high pressure and therefore move upwards along an existing crack, thus shaping the overlaying sediment layers to a dome. Figure 4. The erosion of the sediment dome may be accelerated relative to its surroundings due to the many cracks formed during the uplifting and reshaping process. Figure 4. Formation of a salt dome and subsequent erosion of the previously reshaped, alternating harder H and softer S sediment layers. By this process, the 3 circular water canals, 1, 2, 3, were created. On top of water impermeable layers equals groundwater from far distant mountains is led to the dome. The cracks bring it to the surface as springs. The Semsiat Dome, 50 kilometers west-southwest of Rishat, is a second similar ring structure and has only a 5,000-meter diameter, which is nearer to Plato's figures. Probably those multi-ring dome structures are not so rare and can also be found in other places on the globe. But in the case of Atlantis, the overlaying silt from the deluge may have hidden the ring structures under the surface. The antique Greek city of Helica, destroyed by a great flood in Plato's times, was found just recently under a layer of 4 to 15 meters of silt. Detection would only be possible, if it were on land now, by the use of magnetometer equipment. 5. The springs. And Poseidon himself set in order with ease, as a god would, the central island, bringing up from beneath the earth 2 springs of water, the one flowing warm from its source, the other cold, Crit Myon 3T. These springs produced an abundant volume of water, Crit 117 AB, supplying many different baths for men and horses, watering the sacred grove of Poseidon and delivering water also for the people living on the outer circles of the city. It is impossible that the springs were fed only by the rainwater obtained on the small central island of only 5 stades in diameter. But as described in Figure 4, due to the underground structure of different parallel rock layers, the groundwater can flow over great distances on a water-impermeable layer from the mountains enclosing the plain to the central island on top of the uplifted dome, surfacing there through cracks in the overlaying rocks. It is the same phenomenon as with the artesian wells in the desert regions of the Sahara. Possibly, the warm water comes from a greater depth. In this way, the existence of 2 great water springs on the relatively small central island of Atlantis confirms the above-introduced model for the natural generation of the circular structure of the royal city of Atlantis. 6. Channels in tunnels. The most outstanding characteristics in Plato's description of Atlantis are the many channels distributed around the city and all over the surrounding plain, while Poseidon has created the 3 water rings round the central hill only to provide protection for Plato's home, Crit 113D. Their son Atlas and his heirs connected these water rings and dug a canal from the outermost water circle to the nearby sea coast, Crit Ponson DU15DE. They bored a channel right through the outermost circle, and thus they made the entrance to it from the sea like that to a harbor by opening a mouth large enough for the greatest ships to sail through. The connections are described as follows. They opened out a channel leading from circle to circle, large enough to give passage to a single trireme, and this they roofed over above, so that the seaway was subterranean. For the lips of the land circles were raised a sufficient height above the level of the sea. The land circles were not made of earth, but of rock, as is obvious from the above-mentioned generation model, and also because Plato states that the stone they quarried beneath the central island all round, and from beneath the outer and inner circles, some of it being white, some black, and some red. And while quarrying it, they constructed 2 inner docks, hollowed out and roofed over by the native rock. Crit 116 AB. If the Atlanteans could construct underground docks for their ships, they could as well make the connections between the water rings in the form of tunnels. Plato, who did not see the place and was not an engineer, imagined that they dug out an open canal of the whole depth of the rocky rim, similar to the modern canal through the Isthmus of Corinth in Greece. And afterwards, ship tunnels were known in antique times. Near Naples, Italy, a ship tunnel can be visited, 3 to 8 meters wide, and of a height between 4 and 21 meters, which connected the Roman military harbor in the volcanic Lago d'Averno with the seacoast near Cuma. The ships were not rowed in the tunnel, but punted or sailed. In the tunnel there is always a natural wind movement due to temperature differences between the entrances. 7. Depth of the canals. Back to the canal between the outermost water ring and the sea. According to Crit 115d, it was 3 plethora in breadth, 1 plethron in depth, and 50 stades in length. It had the same depth as the circumferential canal round the whole plain, Crit 118c, which was 1 stadion wide. The length of 1 Greek stadion was, depending on time and region, between 165 meters and 213 meters, the most used value being 185 meters. 1 stadion contains 6 plethora, or 600 feet. These figures for length and breadth may be reasonable, but a canal depth of 1 plethron equals 100 feet, equals 30.8 meters, seems not credible. We must remember the canal had to be dug into an alluvial plain near the sea. In the wet soil, the canal flanks would have slipped down continuously. A canal dug in the soil cannot have vertical sides. This observation was already made by the Persian king Xerxes in 480 BC, described by Herodotus /3/ during the digging of a canal in northern Greece. I will now describe how the canal was cut. A line was drawn across the isthmus from Seine, and the ground divided into sections for the men of the various nationalities to work on. When the trench reached a certain depth, the laborers at the bottom carried on with the digging and passed the soil up to others above them, who stood on ladders, and passed it on to another lot, still higher up, until it reached the men at the top, who carried it away and dumped it. Most of the men engaged in the work made the cutting the same width at the top as it was intended to be at the bottom, with the inevitable result that the sides kept falling in and so doubled their labor. Indeed, they all made this mistake except the Phoenicians, who in this, as in all practical matters, gave a signal example of their skill. They, in the section allotted to them, took out a trench double the width prescribed for the actual finished canal, and by digging at a slope gradually contracted it as they got further down, until at the bottom their section was the same width as the rest. Xerxes Canal, which was found again 1991 to 2001 by a British-Greek team with geophysical survey methods /4/, was 35 meters wide to let 2 battleships pass, but only 4 meters deep. It lies now under a 15-meter thick alluvial layer. For what purpose would the Atlanteans make their canal so much deeper? Their ships, triremes or comparable ships, with 200 seamen, with a draft of 1 to 2 meters, could very well navigate on canals of 3 to 4 meters depth. Compare the trireme in Figure 5. The cargo ships in ancient times were not as big as battleships. A relatively big cargo ship from Roman times was recently found in the Netherlands. It was 25 meters long and 2.7 meters wide, with a draft of 0.7 meters. These cargo ships used on rivers and canals were not rowed, but had sails and were also punted or towed. Table 1 shows the dimensions of some ancient and modern canals. Not until 10 years ago, in 1995, was it possible with modern excavators to make the Panama Canal 1.5 meters deeper. Each meter more of depth increases tremendously the difficulties for the engineers, especially if the soil is alluvial. And the Atlanteans are supposed to have dug canals more than twice as deep as the modern Panama Canal. Moreover, the circumferential canal round the plain, 1,850 kilometers long, would have been nearly 23 times the length of the Panama Canal. This is indeed unbelievable, even if the Atlanteans had our technology instead of the technology of their age, the time of horse-driven war chariots, of stone shooters and slingers. Plato was right when he doubted this information, Crit 118c. But he knew nothing about the construction of canals, and therefore did not know that the reported dimensions were not only incredible but impossible from a technical point of view. 8 dimensions in Atlantis. If we doubt the correctness of Plato's information about the dimensions of the canals, we should have also a look to the other dimensions cited in the Critias. Table 2 shows a synopsis of all these data given in Stades column 1, together with their translation into the metric system, using 1 stadion equals 185 meters column 2. If the plain of Atlantis had a size of 555 by 370 kilometers, it would not be possible to recognize from its center that it is encircled by mountain chains due to their great distance. The total area of the royal city of Atlantis, 443 square kilometers, would have been so great that it exceeded that of today's London with 303 square kilometers and 3.2 million inhabitants. Atlantis? A city greater than today's London? The racecourse for horses, 185 meters wide and 10.5 kilometers long, is extraordinarily large, compared with our courses for horse races with lengths between 1 and 3.2 kilometers. The bridges over the canals have an unnecessary breadth of 30.7 meters. The famous Carolus Bridge, built 1375 in Prague, the then capital of the German Empire under Carolus IV, to connect the 2 parts of the city, is 516 meters long and 9.5 meters wide. To come to terms with these incredible figures, some authors have made different proposals to divide Plato's figures by 2, McCullough /5/, or by 10, Gallinopoulos and Bacon /6/. Does Plato or Solon have something mixed up? 9, Ket instead of Stade. We have indeed an example that a famous Greek author gave wrong information by transforming Egyptian length units into Greek states. This was Herodotus, the father of history, who gave all distances in Egypt in states much longer as they are in reality, while he reported all the distances in Greece correctly. The usual explanation for this error is that he has mixed up the Egyptian units of measurement, obviously taken from an Egyptian itinerary, before he transformed them into states. A similar error could have taken place while the Egyptian priest narrated the Atlantis story to Solon. It is self-evident that the priest gave all the distances in Egyptian units of measurement, as they were written in the ancient texts, and Solon wrote them down as he heard them for later transformation into Greek states. When he returned to Greece, he had no opportunity for this calculation, or forgot it. His heirs, Dropides, Critias the Elder, and Critias the Younger, found in Solon's notes only the figures without the units of measurement, and obviously thought it must be states, especially since in their time, due to the busy trade with the Greeks, even the Egyptian people were using Greek states in addition to their own units, and Critias passed this erroneous information on to Plato. I feel that this is a very probable error in the long chain of tradition between the Saitic priest and Plato. Which unit of measurement was commonly used by the ancient Egyptians? It was the royal cubit, or me, 0.524 meters. And for longer distances, the ket equals 100 royal cubits. 1 ket equals 50, 2.4 meters equals 172 feet. 7. When we take this ket for what Plato called stud, we get much more probable dimensions for Atlantis than those mentioned before. See Table 2, Column 3, A. The size of the level plain is 105 by 157 kilometers, 16,475 square kilometers, a little smaller than the Peloponnesus Peninsula in Greece. B. The diameter of the central city of Atlantis is 6.7 kilometers. The city of Rome in the late times of the Roman Empire, Aurelian Wall, had a diameter of 640 meters. A. The racecourse for cars is 6 kilometers long and about 1 million inhabitants. C. The racecourse for horses is 52 meters wide and 3 kilometers long, like one of the larger modern racecourses. D. The canal round the plain is 524 kilometers long, 52 meters wide and 8.7 meters deep. The forerunner of the Suez Canal, built by Pharaoh Necho and King Darius of Persia about 500 BC, was 180 kilometers long, 45 meters wide, and had a depth of 5.5 meters. See Table 1. E. The bridges over these circular canals are 8.7 meters wide, comparable with the breadth of medieval bridges. F. The Temple of Poseidon has a size of 26 by 52 meters, a very reasonable size compared with the famous Poseidon Temple in Paestum, Italy, 24 by 60 meters. But couldn't it be the case that with the introduction of the ket dimensions, some measures were too small to be credible? Was it possible that on the canal from the sea to the harbor, with a width of 26.2 meters, two triremes could meet? A Greek trireme from classical times was 37 meters long, had an overall beam of 5.5 meters and a height of about 4 meters. The oars had a length of 4.2 meters, but due to their oblique position relative to the surface of the sea, and 1/3 of their length being inside the ship, the horizontal space needed for using one oar is only 2.7 meters. A road trireme needed therefore a space of 2 times 2.7 plus 5.5 equals 10.9 meters. In a canal of 26.2 meters width, 2 triremes could easily pass. See figure 8. Was the central island at 262 meters diameter big enough to contain all the reported buildings? Temple of Poseidon and Clito, Royal Palace, Cretan 116c, separate beds for the kings, for private citizens and for horses, the guardhouse for the most trustworthy spearmen, Cretan 117c, and the sacred grove of Poseidon, Kritos 117b. Figure 7 shows a true-to-scale sketch of the central island. It is obvious that all the cited items could be placed there. Fig. 7. Central island with Poseidon Temple, center. Royal Palace, barracks of the guards, baths, circles, and sacred grove, trees. The Acropolis in Athens, 120 by 280 meters, has an area of about 30,000 square meters compared with 54,000 square meters for the central island of Atlantis. We can conclude that it makes sense to take Egyptian kets instead of Greek states, for getting a better interpretation of the dimensions of Atlantis in Plato's Critias. 10. Dams along the canals. As the canals in the plain of Atlantis lead to the sea, and the sea outside the Pillars of Heracles, Crit 24e, is the Atlantic Ocean, we must take into consideration the tides. The average turn of tides can be 2 to 4 meters, and the canals, at least near the estuary, had to be provided with dams on both sides. The material to build the dams could be taken from the excavated material, and from the cross-section of the canal, we can therefore also calculate the height of these dams. The triangular cross-section of a canal with 8.7 meters depth and 26.2 meters breadth is 114 square meters. Each dam has a cross-section of 57 square meters, and with a side angle of 45 degrees, its breadth could then be calculated at 12.7 meters, and its height 9 meters. With a side angle of 30 degrees, the breadth of the dams is 15.2 meters and their height 7.5 meters. This dam height would be sufficient also in the case of a spring tide. When due to heavy rains in the surrounding mountains the rivers were in flood, the height of the canal dams would perhaps not be enough. But in case of flooding, the Great Plain could serve as a reservoir to accommodate the abundance of water. It is therefore probable that the houses of the farmers in the plain were situated on artificial hills, wharfs. The parallel irrigation canals in the plain had a width of 8.7 meters. The depth is not mentioned, but could be 2.5 meters. Their cross-section would then be 10.9 square meters. The dams on both sides with 30-degree side angles would have a breadth of 6.6 meters and a height of 3.3 meters. 11 mountains in Atlantis. And the mountains which surrounded it, the plain, were at that time celebrated as surpassing all that now exist in number, magnitude, and beauty. For they had upon them many rich villages of country folk, and streams and lakes and meadows which furnished ample nutriment to all the animals, both tame and wild, and timber of various sizes and descriptions, abundantly sufficient for the needs of all and every craft. Crit 118b. They conveyed to the city the timber from the mountains and transported also on boats the season's products. Crit 118e. And the number of the men in the mountains and in the rest of the country was countless. Crit 119a. The first citation is normally interpreted as if the mountains of Atlantis must have been higher than the highest mountains now existing. But I wonder how these Himalaya-like mountains could have had many villages with much country folk, forests, meadows, lakes, food supply, etc. The Cuban linguist Diaz Montexano wrote that the Greek word megatos had not only the meaning of height, but in the above context can also mean greatness or extension, and only this interpretation makes the whole story logical. In high mountains like the Himalayas, rich villages with countless inhabitants couldn't have existed, producing ample nutriment for every animal and timber abundantly sufficient for the needs of every craft. The rich supply of timber would rather speak for mountains of medium height. Not only high mountains, but also highlands are able to shelter the bordering regions from the northern blasts. Crit 118b, as we can see it in the case of Rheingau, one of the warmest regions of Germany with its famous Riesling vineyards, which lies near Frankfurt Airport on the southern slopes of the wooded Taunus Hills. Maximal elevation 880 meters above sea level. It seems that Crit 118b means the whole mountainous landscape was praised for its versatility and its rich settlements and was not surpassed by any other for its scenic beauty. Here, mining in the mountains is not mentioned as a source of wealth of the country folk, but Plato writes about metals to begin with, both the hard kind and the fusible kind, which are extracted by mining, and also that kind which is now known only by name, but was more than a name then. There being mines of it in many places of the island. I mean orichalcum, which was the most precious of the metals then known, except gold. Crit 114e. Mines are mostly situated in mountainous regions, and the rich deposits of a metal nearly as precious as gold must have made the inhabitants of these regions nearly as important as those living in the royal city of Atlantis. It cannot be ruled out that in greater distance from the plain there were also high mountains with perpetual snow on their peaks. It was already mentioned in chapter 2 that the catchment area of the rivers arriving at the plain must have been at least 10 times as large as the plain itself. And Plato's note in Crit 118e that the Atlanteans cropped the land twice a year, making use of the rains from heaven in the winter and the waters that issue from the earth in summer by conducting the streams from the trenches, suggests that the rivers feeding the irrigation canals got their water in summer from the perpetual snow of the high mountains. What about the opinion of some authors that all the high mountains sunk completely under sea level during the destruction of Atlantis, without remainder? It is disproved by the statement in Timaeus 25d that Atlantis in like manner was swallowed up by the sea and vanished. Wherefore, also, the ocean at that spot has now become unpassable and unsearchable, being blocked up by the shoal mud which the island created as it settled down. The reported portentous earthquakes and floods, Tim 25c, greater than the tsunami of December 26, 2004 in Indonesia, flooded the royal city together with the whole plain, leaving behind a shallow sea region where the plain had sunken for some meters. But the mountains could not sink during a catastrophe like this more than the same number of meters. They must still exist today. 12. Irrigation system. Colonization of Atlantis began first on the hill, low on all sides, near the sea coast. Crit 113 CD. Thereon dwelt one of the natives originally sprung from the earth, Evenor by name, with his wife Leucippe. There were 2 springs, used for irrigation the fertile soil, producing out of the earth all food in plenty. Kritos 113e, and they led them to the plantations of trees such as suited the waters. Crit 117a. It is very probable that the first Atlanteans soon began to cultivate vegetables and cereals in gardens and fields. Round the hill stretched the plain, highly fertile as well, Crit 113c, but naturally first without any installations for draining or irrigation. So when the population increased, it became necessary to use also this land for agriculture by digging trenches. This was practically the same situation as in the beginning of most of the known high cultures. People began to build irrigation canals in suitable places, and that way increased tremendously the productivity of their agriculture. Because for this task, a well-planned teamwork was necessary, a central authority became indispensable. In this way, the hereditary kingdom was settled. Plato indicates this in Kriton 118c. Now, as a result of natural forces, together with the labors of many kings which extended over many ages, the condition of the plain was this. But where did the many people come from who were necessary for the first creation of the sweeping canal system described by Plato, when the plain was a river delta, see chapter 2, and originally marshy for the most part? Not many people could have dwelt there except some fishermen. But in the surrounding hills and mountains, there were certainly settlements of men living there as hunters and gatherers or farmers, perhaps also as miners. The king, intending to begin the great project of the irrigation of the plain, could have prompted them with the chance of rich farmland and greater wealth to participate in this task. Each village in the highlands could then have a claim to a certain area in the fertile plain, and the respective leader of the works and the most hard-working participants could settle on the newly created ground, together with their families. This order of events is suggested by the quote in Critical 118e to 119a. As regards their manpower, it was ordained that each allotment should furnish one man as leader of all the men in the plain who were fit to bear arms, and the size of the allotment was about 10 times 10 stades, and the total number of all the allotments was 60,000, and the number of the men in the mountains and in the rest of the country was countless, according to the report. And according to their districts and villages, they were all assigned to these allotments under their leaders. This shows clearly that in later times as well, there existed a close connection between a certain village in the mountains and a certain allotment on the plain, and one leader was responsible for both places and had to recruit 20 warriors altogether from these two geographically separate sites. This means that the supposed 200 people being able to call up 20 warriors would not all have to live on the allotment in the plain having 0.275 square kilometers equal to 68 acres in size. If only half of this population lived on the allotment in the plain, and the other half in the mountain village assigned to it, we get a population density for the plain of 363 per square kilometer, the same as in the Netherlands, a likewise level country near the sea, famous for its irrigation system. 13. Conclusions. It is fascinating how detailed a picture of Atlantis can be found by thoroughly reading the texts in Plato's Timaeus and Critias, considering what they really could mean, and comparing the results with well-known examples from our time. In this way, we have acquired a nearly complete description of the general geography of Atlantis, which can now be used to locate the sunken city. A new and amazing result is that we have to divide all measures given by Plato by the factor 3.5, or in other words, to replace the Greek stade in his narration by the Egyptian ket. All the newly calculated dimensions are credible and probable. In a similar way, it should be possible to find out the exact location of the sunken city of Atlantis and the time of the catastrophe that destroyed it. Egypt being the best candidate, elaborated by Dr. J. Gwynne Griffith's essay.